Let's dive right into this explainer on the grammar of graphics, analyzing the shape of data. Today, we're conceptually mapping out exactly how to think about the shape of your data before you even think about writing a single line of analytical code. Imagine you're mapping out global life expectancy against income. Or consider this, you're looking at a massive data set of 50,000 diamond sales, trying to figure out why the cut quality actually explains shockingly little about the final price. To answer questions like these, you have to start in the right place. As an engineer staring down a literal mountain of raw information, how do you decode it? Well, you do it by mastering how you construct your visualizations. See, we don't answer complex engineering questions by just blindly guessing which chart to pick from some drop-down menu. Instead, we build the plot layer by layer using a very strict grammar. It goes like this. First, the data. Second, a mapping that explicitly links your dataset variables to visual properties. Think coordinates or colors. And third, a geometry that physically draws those properties onto the screen. You add a layer, and the rest just stands. And by the way, this underlying logic works identically in both R and Python. Now, that mapping step, it is absolutely pivotal. In fact, it's a source of most early mistakes. You've really got to understand what varies and what stays completely static. A visual property that's set inside the mapping is going to vary dynamically with your variable. It's like having a color change row by row depending on the continent. But if you take that exact same property and set it outside the mapping, it acts as a rigid constant. It just applies uniformly to every single point on the board. And here's the thing about geometries. Your available geometry is entirely dictated by your variable types. You literally cannot force a shape onto incompatible data. Two numeric variables, they naturally invite points, like for a scatter plot. If you have a category analyzed against a number, well, that invites a box plot to show distributions. And a single numeric variable invites a histogram. Basically, the data types themselves license the shape you get to use. Because a plot is built sequentially from this grammar, it transforms into an actual object you can hold onto in your analytical environment. You can build it, add to it, restyle it, and call it up again instantly. This makes iterating incredibly cheap. Let's say you want to shift the whole thing to a clean, publication-ready look. Well, themes just swap in as another layer sitting right on top of your existing object. But keep this in mind. Labels and readability aren't just finishing touches, they are an intrinsic part of the analysis itself. A figure that a reader cannot decode has communicated absolutely nothing. In systems engineering and data analysis, the figure often is the finding. If your axes like units or legends are nowhere to be found, trust in your relationships evaporates instantly. Clarity really isn't optional here. This whole approach requires a pretty fundamental shift in mindset. Honestly, the most dangerous mistake you can make is treating visualization as an afterthought. It is not mere decoration tacked on after the real mathematical work is done. No, here visualization comes absolute first. It comes first because you must look at the physical shape of the data to know what to compute in the first place. When you plot those 50,000 diamonds and suddenly spot a distinct curve in the scatter plot, that visual shape is exactly what dictates your mathematical model. You map the variables, you observe the physical shape, and you let that geometry dictate your next analytical move. As you look at the analytical work ahead conceptually, you need to know how to contrast a sensible result with a suspicious one. A totally sensible result is one where the geometry perfectly reflects the underlying variable types. The labels are clear, and the visual shape explicitly drives the computation. On the flip side, a suspicious result forces visual properties outside the mapping. It features unreadable labels, or just blatantly crams mismatched data types into shapes where they absolutely do not belong. So, moving forward, keep your focus incredibly tight on what actually varies versus what is just a constant. Watch out for unmapped constants disguised as variables and geometries forced onto incompatible data types. When you face your next massive dataset, ask yourself, are you truly mapping the dynamic variation of your system, or are you just painting rigid constants onto a canvas?